what I'm going to talk about today is implementing snow temperature analysis in the global forecast system. First of all, the background. As we all know, land-atmosphere interactions are very important for regulating surface energy fluxes and moisture exchanges, but they are often treated independently in the DA frameworks of most NWP models or NWP systems. Um, that is using different DA methods to assimilate different observation data sets for land and atmospheric components. So this is a practice called weakly coupled DA. On the other hand, a few research have illustrated that strongly coupled DA offers improved representation of land atmosphere coupling, that is using the same DA method to assimilate the same observation data set for both land and atmospheric components. So the motivation of our research is that because NOAA GFS also uses the weakly coupled DA method, that is the GSI-based hybrid 40-in DA method. It uses 40 to update high-resolution deterministic forecast, uses the ENKF to update lower resolution forecast for 80 ensemble members for the 40-in DA method. For the linear DA part, it relies on direct insertion of observed products and model integration with observational forcing. So Clara Draper tested strongly coupled DA by extending the ENKF to linear DA, mainly the soil part, and found that it can improve soil temperature and moisture analysis. So for this research, we extend Draper's research by adding snow temperature analysis to the GFS for better land surface representation. Both cryosphere and soil. So here it's schematic shows our goal. So basically, we want to use the strongly coupled DA that it's use the GSI ENKF, the same method, to assimilate the same observations to update both the atmosphere and land variables, including snow and soil variables. Specifically, we just want to update the uppermost snow layers because it's closest to the atmosphere. So it could be the first layer when it's only one snow layer, and could be the second layer if there are two layers. It could be the third layer if there are three layers. So this is the flow chart for updating the GFS code, mainly the GSI ENKF. So the first step is to get the snow temperature in the history file, because we need this as the background. And then we create a snow mask based on the snow temperature. And the third step is to process the observations. And then we can get the snow temperature increments based on the snow mask, background, and observation. Because the GSI ENKF, it's in the Gaussian grid, so we need to regrade the Gaussian grid increments to the GFS cubed sphere model grid. And then, based on the increments, snow mask, as well as the background, we can get the snow temperature analysis by adding the increments to the background. So after updating the code, we designed two experiments to test the if the code update is correct or not. So the first one is the control experiment. It doesn't analyze any variables. The second one is the snow analysis experiment. It analyzes the snow temperature. The uppermost layer snow temperature. So we use the GFS version 17 as the test model, and the resolution it's C96, which is 1 degree for both the deterministic forecast and the ensemble forecast. And it has 127 vertical atmospheric layers, 4 soil layers, and up to 3 snow layers set up in the NOAA 96 model. And the simulation period is from October 1st, 2022 to October 10th, 2022. The initial conditions, it's downscaled from the restart files from the operational GFS on October 1st, 2022. We also replaced the land variables by running the offline NOAA model for 30 years. I mean, to replace the land variables in the original restart files from the GFS. The simulation datasets are the standard atmospheric observations from the operational GFS. And also we added the screen level observations, mainly the temperature and humidity. So here, this figure shows the first layer snow temperature, which is the lowest layer that is closest to the land surface. So by doing this, we just want to make sure the code update is correct. We want to see if there are any weird value, and if the spatial distribution is correct. So the left panel shows the result of the control experiment, and the right panel shows the differences between the snow analysis and the control experiments. And this one is for the snow cover, and this one is for the snow depth. So basically, we plotted all figures for all simulation cycles from October 1st to October 10th. And so everything looks normal, so that's great. So we are planning to do the next step. To summarize, the GFS code, mainly the GSI ENCAVE, was updated for snow temperature analysis, preliminary evaluation of land variables. Actually, not only snow temperature, snow cover, snow depth. We also tested the soil moisture, soil temperature, and also the 2-meter air temperature. Yeah. Basically, the evaluation shows that the code update is reasonable, and a more rigorous scientific evaluation comparing land and atmospheric variables with independent observations is still ongoing. Hope that we can get some good results from paper. All right, with that, I'll stop here and take any questions you might have. Thank you for your attention.